So this lesson will deal with actually how we measure motion. So the question that we're kind of trying to answer today is how are speed and velocity different? And we'll also get into the calculations of speed and velocity. So if you think about speed and velocity, we often use these terms interchangeably, but they're really not. And it's a very similar relationship to what we had just talked about with distance and displacement. So let's talk about speed first. Speed is when we have any change in distance over time, and that is called a rate. So a speed is the rate at which that distance is traveled. So how fast we cover a certain distance. Now, there are other types of rates that we have. In other words, like rates of reaction, how fast a chemical reaction proceeds. But in this case, we're talking about traveling a distance in a certain amount of time. Now, let's compare that with velocity. Velocity includes the speed, but very much like displacement, it includes the direction of its motion. So velocity is a vector quantity. So even if our speed remains constant, our velocity can change if the direction of that speed does change. And we will see that when we talk about a specific case. So velocity is a vector quantity, just like displacement. Now, speed and velocity we can actually calculate, and usually when we calculate it, we don't differentiate between the two. The formula for calculating speed or velocity is v equals d divided by t. So the reason why we use that v is because that stands for velocity or for speed. The d is the distance and the t is the time. Now, these distance and time units can really be any distance unit and any time unit. So speed always has a unit that has a distance unit divided by a time unit. Like I said, these can be any of them. Examples include things like meters per second, meters over seconds, kilometers per hour, or centimeters per year. We have things that move at meters per second, for instance, cars. Kilometers per hour also we could use with cars. That's usually how we calculate things. Centimeters per year would be things like our tectonic plates in the Earth's crust. So we have a number of different uses and a number of different units that we can use, and we just try to choose one that is appropriate. Now, we have some different variations on speed. We can talk about something being a constant speed. And this is what happens when the speed of an object does not change over time. For example, the car speedometer reads 65 miles an hour for an extended period of time. And we've all had that happen where we've been in a car, let's say on the highway, and we're going a constant speed for a very long period of time. That does happen. But my question to you is speed usually constant? And the truth is, most of the time, it's not. So let's look at a really short scenario here of how speed is not a constant thing. So let's say that we took my speed, or my husband's speed actually, when he goes to work. So at time equals 0, which is right here, okay, he pulls out of the driveway, and in kilometers per hour he accelerates. Okay, and then he kind of levels off his speed. And then he has to slow down because he's going to turn onto the highway. And then he increases his speed again. And again, he stays for 4 or 5 minutes at that constant speed. And then he comes up to some traffic and he's behind a slow truck. And then he has to increase his speed to try to get around that truck. And then as he's coming into town, he slows down and eventually stops at the stoplight by his work. So as you can see, because the speed is going up and down all over the place, it is not constant at all. So sometimes measuring speed in terms of constant speed is not very convenient. So a lot of times we refer to things in terms of its average speed or its average velocity. Okay, so this is the way we describe it when it's going to be changing and not staying constant over a particular distance. We calculate it exactly the same way. The v equals d over t, but this time it is the total distance divided by the total time. So the equation looks just a little bit different. We can also look at something called instantaneous speed or instantaneous velocity. This is the speed of an object at any one point in time. So you glance down at the speedometer on your car and you see that you're traveling at 35 miles an hour. Well, that could be changing. And so that is that instantaneous speed. That specific moment in time is that speed. Now we can also calculate motion and speed off of graphs. So when we graph our motion, so when something speeds up or slows down, its instantaneous speed is constantly changing. Okay, and that's like the example we were talking about. When something is slowing down and speeding up, its instantaneous speed is constantly changing, but its average speed should stay close to the same. Alright, now like on the example I showed you with my husband on his way to work, we can graph our motion. So when we graph motion to calculate speed, we use a distance versus time graph. So time is on the x-axis and distance is on the y-axis. On a distance time graph, when I take the slope of the line, that represents the object's speed. And so the greater the speed, the steeper the slope. If I see a horizontal line on the graph, on this distance time graph, it means my distance isn't changing, so I'm not moving. So when I set it up, okay, distance is always on the y-axis and time is always on the x-axis because we can graph this. So let's go through a couple of examples here. And using the graphs provided, we are going to calculate the speed. So let's take a look at this first one here. Okay, so I've got a distance time graph here, and as you can see, I actually have some information here about the slope. Remember, the slope is referred to as the change in y over the change in x. And if I look at my graph here, I actually can see it's marked two changes. Okay, this distance here to here is 10 seconds, and this from here to here represents 250 meters. So we've actually already done the calculation in terms of the change in y and the change in x. So all I have to do is divide those. So my speed would be equal to 250 divided by 10. And when I do that, I would get 25. And in this case, the unit is meters over seconds. Now, you're also probably looking at this and going, we're doing calculations. Do I need to include sig figs? And absolutely you do. In this case, my final answer will actually only have one sig fig because number 10 here has 1. So when I round this, this would be 30 meters per second, and that is my final answer. If we take a look at the second graph, okay, again, they have the change in y over the change in x for us. So my speed is equal to 125, and my unit is meters, divided by the 10 seconds. So my speed, when I plug that into my calculator, would be 12.5 meters per second. Now, I need to take this down to 1 sig fig. So with sig figs, it would be 10 meters per second, and I am done. The last one that I have a variable speed. Now this variable speed makes things a little bit interesting. I have two different speeds because I have two different changes here. And if you do those calculations, you will see you will actually get two different speeds because I have this time of no movement here with that horizontal line. So one thing, when you have that varying speed, remember you want to calculate the average. So let's do that. Instead of calculating two different speeds, let's calculate the average. So over 20 seconds, I travel 500 meters. So my speed would be 500 meters in the span of 20 seconds. So my average speed is 25 meters per second. Now again, I need to make this into the correct number of sig figs, so I need to round this to 30 meters per second because each of my measurements here only has one sig fig. So that's how we can actually calculate it using graphs. Now, sometimes you may have to do something like this, but oftentimes you will actually be given word problems, and we'll go through that here in a moment. Now, circular motion. This is the one I was talking about in terms of velocity. If you're moving in a curved path, your object is actually changing its velocity, even if it's at a constant speed. And that's because as you go around, you are changing the direction. An example of this would be like a car, for instance, on a racetrack. As it goes around the corners, its speed may stay constant, but its velocity is changing because it's changing the direction of its movement. All right, so let's take a look at some practice problems here for speed. So the first one, while you're traveling on vacation, you measure the times and distances traveled. You travel 35 kilometers in 4/10 of an hour, followed by 53 kilometers in 0.6 hours. What is your average speed? So I have to calculate the average speed. So this here represents my total distance. So I have to take those two distances and add them together. And then on the bottom here, I have my total time. So 53 plus 35 gives me 88 kilometers. And when I add 0.6 and 0.4, I get 1.0 hours. So my speed is going to be 88 kilometers per hour. Now, if I look back at my measurements that I took, though, both of these each only have one sig fig. So with correct number of sig figs, this would be 90 kilometers per hour, and that's my final answer. Let's take a look at another one here. This is another average speed problem. A person jogs 4 kilometers in 32 minutes, then 2 kilometers in 22 minutes, and finally 1 kilometer in 16 minutes. What is the jogger's average speed in kilometers per minute? So here I have to add 4 kilometers plus 2 kilometers plus 1 kilometer. That is my total distance. And I'm going to divide that by my total time, which is 32 minutes plus 22 minutes plus 16 minutes. When I add up across the top, I get 7 kilometers. And when I add up across the bottom, I get 70 minutes. So when I take 7 kilometers and divide it by 70 minutes, I get 0.1 kilometers per minute. Now I do need to take a look at sig figs here. all of my measurements back here have 2, but my answer as I have it written only has 1, so I need to put a 0 there. 0.10 kilometers per minute is my correct answer. Let's take a look at another one. A train is traveling 190 kilometers in 3 hours and then 120 kilometers in 2 hours. What is its average speed? So I take 190 and I add 120 and I divide that. I take my total time, 3 hours plus 2 hours. So when I add 190 and 120, I get 310, that's kilometers, in 5 hours. So when I do that on my calculator, I get 62 kilometers per hour. Now if I check my sig figs, 2 sig figs, both of those have 2 sig figs, so my answer as it comes out on my calculator stays the same. Now, in all 3 of these problems, we have solved for speed. Okay. Now, we can solve for speed a little bit easier. In these, we've had to add. But in other problems, sometimes we don't have to add. For instance, with this one. What must your average speed be in order to travel 880 kilometers in 8.1 hours? Okay, so I have, All right, so I have 880 kilometers that I am traveling in 8.10 hours. All I have to do, I'm given a distance and a time, and all I have to do is divide those on my calculator. Now when I do, I get a really nasty decimal. I get 108.641975.3. So let's look at sig figs. My answer can really only have 2 sig figs. So I know I'm going to cut the answer off here. This 8 is going to round that up, and that will actually help me because when I write 110, I have 2 sig figs, and my unit is kilometers over hours. Now with this last problem, there's a couple of things here that are a little bit tricky. First of all, you're given the speed. So what that does is it means that we're not solving things like we did before. Okay, we're solving for something other than speed. If you look at the problem, it asks for how far. When you're asking how far, you're actually talking about a distance. So if you think of our equation, we had V equals D divided by T. And actually the setup of this is very similar to our density formula that we did a couple of units ago. So we can actually set up the triangle like this, with D on top and V and T on the bottom. In this case, we're solving for the D, the distance. So in order to find that, we take our speed and we multiply it by our time. That's pretty simple. However, if you look at the unit for our time here, it is in minutes, whereas the unit of time here in my speed is in hours. So I have to get them to the same unit first. So first thing I'm going to do is I'm going to take my 175 minutes and I'm going to use factor label method to turn that into hours. My minutes will cancel, and then I take 175 times 1 and divide it by 60, and with the correct number of sig figs I get 2.92 hours. Now that I have the time in hours, I can then take the velocity and multiply it by the time to get the distance. So my speed was 11.8 kilometers per hour. I'm going to multiply that by 2.92 hours. And when I multiply that together, I get 34.456. And the unit is actually going to be the distance unit that comes from here, which is kilometers. Now, I do need to record this in the proper number of sig figs. This has 3, This one has 3. So my final answer has to have 3. So I'm going to cut this off here. I look one space beyond it. It's a 5. So it will be 34.5 kilometers. Now what you have to kind of finish off this section in terms of practicing with speed, you have a worksheet that has some pair practice problems which you can complete and check with the answer key that's been provided on Moodle. In addition, you have a homework worksheet that will be due.